Okay, so let's start. In the first part of this lecture, I want to explain how to use the specialization theorem, and then I want to discuss some of the homework problems. How to use theorem. Okay. Last time we discussed that how a curve over, say, f q bar smooth that for any curve over fq bar, smooth projective curve, that any curve can be lifted in characteristic 0. Then there exists a curve x, smooth projective, x over spectrum of the Witt vectors. Let me call this field K. And this will be my A, discrete evaluation ring, such that its x tensor or A with K is x0. And now we are in the situation where we can apply this specialization theorem. So, well, a bit another piece of notation. K will be the fraction field of A. So this is the periodic completion of the maximal unramified extension of QP. We have the fundamental group pi1 et al. Of x over k bar. And the specialization map goes to pi1 et al. Of x0. That's already over an algebraically closed field. This is specialization. And we know that this group is, this homomorphism is surjective. And so this is the fundamental group of a curve over an algebraically closed field of characteristic P. That's what you want to compute. And this group is what we know. So, well, how do we know this? It's a curve over an algebraically closed field of characteristic 0. And so there is a general theorem. So that reduces, in particular, the computation of this group to the case of curves over the field of complex numbers. So the general theorem is the following. Suppose I have two algebraically closed field and, well, an arbitrary field extension. Of course, it's not algebraic unless it's trivial. And suppose I have some scheme of finite type connected finite type. Then we have, we can make the best change to k bar over k. This maps to y, and I can look at the corresponding map on the étale fundamental groups. Well, then there are three assertions. So, well, first, let's give a name to this. Phi is surjective. And secondly, phi is an isomorphism if one of the following two conditions is satisfied. If y is proper, or characteristic of the base field is 0. So, well, part A and half of the part B is, was in the homework assignment, and I plan to discuss this today. So the fact that phi is an isomorphism for proper schemes in characteristic P is required. Well, it requires another idea. I will defer this proof for later. So let's use it. K bar is well, it's an algebraically closed field of characteristic 0, and its cardinality of this set is continuous, so it can be embedded into the field of complex numbers that exists such an embedding. And so I'm in this setting, and in particular, so it's the theorem applies. So I don't even need properness here because we're in characteristic 0. So pi 1 of pi 1 étale of x k bar is isomorphic. The map goes this way. It doesn't matter. Pi 1 étale x c. This group, well, we know what this group is. It's a profinite completion of the topological fundamental group. So if G is genus of x0, then this is well, free group. So pi 1 étale xc is free group on generators A1, B1, AG, BG, modulo single relation that A1, B1, A1 inverse, B1 inverse, AG, BG, AG inverse, G inverse is 1. So you take the smallest normal subgroup that contains this element, and so this is a discrete group, and the étale fundamental group is its profinite completion. So this describes this group abstractly as a topological group, but well, this group has a lot of extra structure that is not visible from this description. Namely, the Galois group of k bar over k acts on the category, it acts on this scheme, and therefore it acts on the category of finite étale covers of this scheme. And so since it acts on the category, it acts on the fundamental group. Well, there is some complications here. So it acts on the category, but it doesn't preserve the fiber factor, the action of the fundamental group, of the Galois group, right? The fiber factor gets also twisted. But we know that the fundamental group does not depend on the base point, on the fiber factor, up to conjugation, up to inner automorphisms. So this has action of the Galois group by outer automorphisms. So this is, well, a remark is that we have the interesting additional structure this group has is action of k bar over k to automorphisms, outer automorphisms of pi 1.
X has lots of rational points, right?
X has a lot of rational points, right? That's true.
So can't we just?
We can reg it, but then the actual action will depend on the choice of this rational point. So okay, so another way of seeing this action is via the last exercise from the homework assignment. So here is the last exercise. So you can take the fundamental group of x k bar. By functoriality, it maps to the fundamental group of k, of x k. And this scheme maps to spec k. So by functoriality, you have actually mapped to pi 1 étale of spec k, which is nothing else but the Galois group of k bar over k. And so the last homework problem asserts that this is a short exact sequence. And whenever you have such a short exact sequence, this group acts by auto-automorphisms on normal subgroup, right? That's a normal subgroup, so you just take an element here, lift it, and then act by conjugation. That's a well-defined auto-automorphism. But if you fix a k point on xk, then it gives you a section which makes this into a semi-direct product of this group and this group. And then it gives you an actual action of this group here, but it depends on the choice of a point. So, well, there is a whole theory. Well, so this section is interesting to describe. So it's you know abstractly the group, but how the Galois group acts, well, it depends very much on your curve, not only on its genus. It's not. It's really sophisticated, a fine invariant of a curve. Okay. So very good. So now this is a remark. So now specialization theorem asserts that this is surjective map, and it's also isomorphism on co-prime to characteristic quotient. So let's introduce some notation. So definition. So let G be a profinite group and let define G prime to be, this is also a profinite group, so denote by G prime the maximal co-prime to characteristic of K quotient of G. So what this is, so G prime is by definition limit. It's a topological group, which is limit of G mod H, where H is in G is open. In particular, it has finite index, normal. And index is co-prime to characteristic, right? So with this notation, the main theorem that we proved is that this map induces an isomorphism on co-prime to characteristic quotients. Okay. So in particular, this group depends only on the genus of the curve and not on the curve itself. And if you, however, I quoted a theorem of Reynaud that says that if you look at this larger group, then it determines the curve uniquely up to finitely many choices. So the map that takes a curve of genus greater than 1 to a profinite group, which is this group, this map, is finite to 1. So there are only finitely many curves of genus greater than 1 over F cube bar with given fundamental group. So this group carries a lot of information, but not its proper quotient. Okay, so this is one application, serious application. Another application is, well, it's a very basic question. So let me keep this. Imagine that you have a family of algebraic varieties over an algebraically closed field. So example 2, application 2. So let's see what I have here. So X over C, suppose I have a family, so smooth proper, and well, X and C are finite type over algebraically closed field. And then, well, I also assume that it has connected fibers, because I will be interested in fundamental group of the fibers, this connected fibers. And then for points C1, C2, in C, yeah, and say C is connected also. So I could say X is connected. Okay. Oh, so for points, I can consider fibers. So these are smooth varieties over K bar over K. So to close it. So, and I'm asked what is the relation between the fundamental groups. Well, so this is a natural question because if my base field again is the field of complex numbers, then it's known that well, any smooth proper map is topologically a fiber bundle. In particular, all the fibers are homeomorphic. So, and in particular, it shows that the fundamental group and their finite completions are isomorphic. So you can ask whether anything like this is true over a field of characteristic P. Well, of course, fibers are not in general isomorphic as algebraic varieties. You can have a non-trivial family of elliptic curves. And we already know that in general, the answer will be negative. These groups are not isomorphic. For example, you may have a family of elliptic curves such that for some C1 in the base, your curve is supersingular. So then the P primary part of the fundamental group is trivial, tal fundamental group. And for, say, you can take C2 such that the fiber is a non-singular, non-supersingular elliptic curve, and then you have P torsion points, and then the fundamental group is larger. So in general, they are not isomorphic, but I claim that theorem is that pi1 et al. That they are co-prime to characteristic P quotients are still isomorphic. Okay? So, and here is a proof. Oh, yeah, so I need to put prime here. So that's as much as we can expect in general. Okay, so proof is very simple, modulo the results that are already at the blackboard. So first of all, we may assume that C is a smooth curve. Well, because if you have any 2 points, you can connect them by a curve, or by a chain of curves in general, maybe, but it's good enough. And even if your curve is not if your curves are not smooth, pass to normalization, pull back to normalization. It will not change the fibers. So, so you have 2 points, and let's so нормализацию рассмотреть кривой. Ну, в смысле, что вот у тебя x на c, а тут вот есть нормализация, и возьми x. Ну, нормализация кривой всегда гладко, потому что одномерная схема, которая нормальна, вообще нет, конечно. So for curves, there is a very simple resolution, functorial resolution of singularities, normalization. Okay, so let's denote by k, capital K, the field of rational functions on C. Then I have every point on my curve defines a valuation on this K, right? The order of the function, rational function at this point, and I can take the completion corresponding to this valuation. So Ci is, well, another way of defining this is you take a local ring of your curve C at point Ci, right? This is a discrete valuation domain. You take its completion with respect to the maximal ideal and take the fraction field. So if you choose a uniformizer, a generator of the maximal ideal, then this gets identified with the field of Laurent series in one variable over K. So, okay, so this is a field which contains K, and I also fix an embedding of the algebraic closure of this field into algebraic closure of this guy. And then we'll look at the, so yeah, maybe another piece of notation. So xk bar will be x times spec k bar. K is a generic point, so this maps to C. This is the geometric generic fiber of my curve. And then we have pi1 et al. Of x k bar. And so for every Ci, it maps to, well, there is this map in this direction, pi1 et al. X k bar Ci. Right? So this map is induced by the inclusion. And then from here, we have the specialization map, right? I take this for my discrete, complete discrete valuation ring, this guy. We have the map from here to pi1 et al. On xci. So this first map is an isomorphism by part B of this theorem. The fiber is proper. And by the way, part B is not an easy theorem. It's relatively easy modular results that we already know. But I will explain. It requires another idea, new idea. So I will explain it later. So this is an isomorphism, and this is an isomorphism on coprime to characteristic quotients. So we get that this group is identified with this. So, well, this, we produced an isomorphism. As you see, it's not canonical. It depends on some embeddings like this. So, and if you kind of careful about choosing these embeddings, you may show that this isomorphism is canonical provided that you choose an étale path joining these 2 points. What is an étale path? You have a scheme, you have a two points with geometric points. What is an étale path? An étale path is just an isomorphism of the corresponding fiber factors. So, well, as in topology, this isomorphism depends on the choice of homotopy class of paths from C1 to C2. A substitute for this in algebraic geometry is an isomorphism of the corresponding fiber factors. Okay. So now that's kind of the 2 applications that are most important. And now I want to talk about, I want to in particular prove the theorem about the base change, the one that I just erased, that I'm erasing, in the case of in-characteristic 0. So I want to do some of the homework problems. Okay, so homework. Let's start with 1. And that was the following problem. So we have algebraically closed field K and any field extension, which is also algebraically closed, and Y over K is connected. Well, it's a scheme of finite type. Then the claim is that if Y is connected, then Yk prime is also connected. So, well, so first of all, I want to reduce it to a more geometric statement. So let's see what does it mean for a scheme to be connected. It means that if you take the algebra of global functions on this scheme, K prime, sorry, this is OY, then it has no non-trivial idempotence, right? If it is disconnected, you can take function which is equal to 1 on one component and 0 on other components, and vice versa. So we want to understand, we want to show that this algebra has no idempotence except 1. Is it clear? Okay. So now, what is this? This is just global functions on Y, tensor it over K by K prime. And now, this is equal to the limit, directed limit, over all subalgebras of finite type over K, right? So finite type means finitely generated. Yes, I can write any field extension as direct limit. I can write K prime as direct limit of A, where A runs over all subalgebras. So I can write it as gamma y or x or y tensor over K with A. And so, therefore, it suffices to prove that this guy has no idempotency. So, and these are just functions on y times spec of A. And A is a domain because it's a subalgebra of a field. So, therefore, it suffices to show, we reduce to showing that product of two connected varieties over an algebraically closed field is itself connected. So, therefore, it's enough to show that for connected x and y over K, x, y is connected. And there is here is a very short, simple geometric argument for this that I learned from Stepan. Simpler than the one in much shorter than more understandable than the one in Steck's project. So what you do is the following. So you so the main observation is that for schemes of finite type, the set over an algebraically closed field, the set of its K points is dense in X. And this is a reformulation of Hilbert's Nullstellensatz. And therefore, so having this in mind, let's imagine that X times Y is not connected. And then I can write it as a disjoint union of two closed subschemes. And so non-empty. And because of this, there is a K point, which is the set of K. Well, in particular, the set of K points is non-empty. So there is a K point here and a K point here. So, OK, so I can pick point x1, y1 here, and x2, y2 here. Then I will draw this. I look at this. So this is a complicated topological space, but its K points is just the product. So I think of, well, I draw a picture of the product of K points. So here is my point x1, y1, and here is the point x2, y2. And by my assumption, they live in different connected components. However, there is definitely a connected scheme, namely this fiber and this fiber. So the union of, so these are the two fibers, two copies. This is a copy of y. This is a copy of x. This is y, x1, well, y. And this is x, And this is not a disjoint union. They intersect at this point. So the union as a subscheme, so this is sort of X union Y. This is a closet subscheme of X times Y, and it's connected. And so that means that, well, the 2 points cannot live in different connected components. Good. So this completes the proof. Now, the next assertion is that so let's say this will be A, and this will be B. So now I fix some X over K. Still, I'm in this setting. So connected. And then the claim is that pi 1 et al. Of X K bar, or K prime, this map is surjective. So then this is surjective. Okay? So first of all, we have to reformulate this condition on the fundamental groups in terms of covers. What does it mean? That so you have two Galois categories, a functor between the Galois categories, and compatible with the fiber functors, and we want to understand what does it mean for fundamental groups, for the corresponding map between the fundamental groups with surjective. So what is the answer? So for any connected y over x, y prime is connected. Right? So and then once we have this, B follows from A immediately. Okay? Good. So now C. So I want to prove half of part B of the theorem. So here we assume that characteristic. By the way, how to prove this? That the equivalence. Well, sort of, I guess.
So assume that it's not surjective.
Yes.
Then, if we interpret both sides as compact topological groups, the image is
Compact is closet, right? It's also Hausdorff, therefore.
so its complement is open, and therefore there exists. So what is the base of open sets? The base of open sets is formed by cosets of subgroups of finite index.
Yes. Mm-hmm.
So there exists a subgroup of finite index in the right group such that so there's a finite quotient of the right hand side, but the image is not everything.
Uh-huh.
And this gives you by Galois correspondence a cover which so then let the right hand side act on this quotient G. This action by Galois correspondence gives you a connected cover because the action is transitive. it's not surjective, therefore the left-hand side action is not.
So kind of informally, what you do the following. You take pi1 et al. 1 x, model the image of pi1 et al. X k prime, and you think of this as a set is left action of this group. The section is transitive. Now, well, I would like to say that it corresponds to a cover, and then if you pull back this cover to x k prime, well, then it's going to be disconnected because the action of this group here is definitely not transitive, since you have point 1, which is stabilized by this action. So this is not a correct argument because this set need not be finite, but as Stepan suggested, there is a way to correct it. It's purely general topology. Okay, so now I'll assume that characteristic is 0, and here is the statement that, well, k is algebraically closed, that pi1 of x times y, x comma y, is, well, let me ignore, just for brevity, the base points. So it's via projections, it's isomorphic to pi1 et al. Of x times pi1 et al. Of y. So this is a deep theorem because it's not true in characteristic P. So there is something that means that we have to use something to prove it. And as far as I know, there is no algebraic proof of this result. All known proofs go through reduction to complex numbers, where the corresponding fact is easy because you can interpret classes in fundamental group as loops, maps from S1 pointed maps. And then, okay, so let's see how the reduction works. So, well, first of all, I want to reduce to the case when K is finitely generated field over Q. So, so the reduction, so step 1, reduction to K in C. So this can be done as follows. So if you consider the category of schemes of finite type over K, then this category, this whole category can be written as inductive limit. One has to think a little bit what an inductive limit of categories is, but there is, after some thoughts, you can come with a definition. So of categories of schemes over K prime, where the limit is taken over all finitely generated subfields. So, for example, if your scheme is affine, then yeah, finite type, yes. So Well, there is a functor in one direction. So if you have a scheme on K prime, you can make a best change and get a scheme over K. And in particular, I'm saying that any scheme of over K can be obtained by this construction from some finitely generated K prime. So for example, if your scheme is affine, then it's a spectrum of a finite type algebra, so it has finitely many generators and finitely many relations. The coefficients on these relations are in K prime, but you can find a finitely generated in K, but you can find a finitely generated subfield such that all the coefficients are in fact in K prime. So your algebra is obtained. You can write the same relations, the same generators and same relations, but over K prime. And then you reduce general case to affine by choosing covers. So, okay, and using this fact, you can conclude that pi 1, so let's see here. So, so this fact reduces the proof to the case of finitely generated subfields. So, well, it's a long kind of, I will not write down details here. Every step follows from this. So, for example, you start with a scheme over K. First, you want to write the claim is that it's defined over some finitely generated subfield, K prime. Then you look at the category of finite covers over your scheme X, which is over K. And inside this category, you have, so you write X as, which is over K as some X prime tensor K over K prime. And then you look at the category of finite étale covers here. You have the category of finite étale covers of this scheme, which is not, of course, the category of finite étale covers of X, but its inductive limit of the category of finite étale covers of X prime best change to some larger finitely generated extension. That also follows from the equivalence I wrote down. So, and then it follows. So, okay. Let's assume that we are done with step 1. Now, let's prove so, well, step 2, which is really the most important, but it will be very short. The statement is OK for K equal to C. And that's because of the comparison with the profinite completion of the topological fundamental groups. And now the reduction, so K and C. And here we will do the following. So let's pick some points, x, y, k points in x, y, k. And then I have a map from pi 1 of x to pi 1 of x times y. So this is base point. So it's induced just by inclusion of x into x times y, given by this point. And also I have this. And, well, a key assertion here is that the images commute. Well, that's actually an inclusion, because if you compose this map with the composition, with the projection, you get identity. So that's also an inclusion. So if you have some element gx here and gy here, then what we want to show is that gy is equal to gy gx. And this is also a deep statement. It's not true in characteristic P. Innocent looking statement. But the proof is not that hard. So what you do, you just look at the diagram. So you have surjections from pi1 et al. Of xc to pi1 et al. Of x, and also pi1 et al. Of yc. And here you have gy, and you pick arbitrary preimages. Well, and also here. This sits here, and this is gx tilde sitting here. And then you know that g1 gx tilde gy tilde times gx tilde inverse gy tilde inverse is 1 in pi1 et al. Of xc times yc. All right, because you know the step 2. And then project to pi1 of x times y. And you get the state. So we are done with the claim, and now we have map from pi1 x times y to pi1 x times pi1 y. That's given by projections. We want to show that this map is an isomorphism, but we just constructed the inverse, well, a map in the other direction. Right? So once we know that the groups commute, it gives a map from the direct product given by the inclusion. So so the composition in one direction, if I go this way and then back, is it will be identity. So it suffices to show that this map is surjective. So let's give a name to this, and the claim is that phi is surjective. Right? This will prove that both maps are isomorphs, mutual inverse. So, and the surjectivity follows from the following diagram. Again, you do the base change, and you have this map, YC, and this map is, this is surjective, this is surjective, and this is an isomorphism. So by diagram chasing, you get that this map is surjective. So good. Now, so let's so this is A, B, C, D, and D was the following statement that so for incharacteristic 0, if you have an extension of algebraically closed field, then the map from pi 1 x k prime to pi 1 et al. Of x is an isomorphism. And so okay, what does it mean? So so it suffices, we already know surjectivity, and it suffices to show that every any cover of xk prime has the form x, y times over k prime for some cover y over x. Okay? So and let's do this. That's already formal from the previous part. Choose some finitely generated algebra A over K with K and K prime such that this cover extends such that my cover of xk prime is obtained by the base change from some cover of xa. So this is y prime such that, and this is the base change. So this is x xk prime xa y prime, and this is our cover. Again, using this fact about the inductive limit of categories, you can always find a finitely generated A with this property. Now, so pick any k point, any homomorphism from A to K. So any k point of spec A. Then this gives me a map from X to this scheme, right? It gives me a map from spec A to spec A, and I can just take the base change. This is base change X. Let's here over XA. Okay. So restricted. So what we produced is a cover of X, and I claim that this has the required properties. So if I take this cover of X and I pull it back here, I get the cover I started with. So why that? Okay, so when proven this, okay, I may assume by large than A that my y prime, so remember that I have a point, k point of x. So x also, yeah, I have a k point of x. So that gives me a map from spec A to this guy. So, and without loss of generality, I may assume that the restriction of this cover to spec A is trivial. Well, why can I assume this? Because I can, if it's not the case, I can construct a cover over spec A, which still maps to k prime, so that this is true. All right? Okay, because k prime is algebraically closed. So any cover of k prime, of spec k prime, is trivial. So that means that there exists a finitely generated subalgebra of k prime, which contains A such that the pullback of this guy is true. So, and now I claim that under this extra assumption, I claim that, so what did I do? So I have my XA, which is nothing else but X times spec A. And so this is the picture. I have this cover of the product. And I first restrict, so it has, this is X and this is spec A. So I have this cover. It has the property that its restriction here is trivial. And it also has the property that, and now what I do, I take this cover, I restrict it to this vertical line. I get a cover of X, and then I pull it back to X times spec A. So I get a cover of X times spec A, which is constant in this horizontal direction. And I claim that I recover my original cover, that any cover of the product, which is trivial on this one horizontal slice, is pulled back from X. And that's true because if you have that follows from this isomorphism. Because if you have a set with an action of this product such that this group acts trivially, then, well, it's the corresponding cover is just pulled back from X because all you have is action of X. Again, it's totally false in characteristic P. So then I claim that y prime is equal to this y prime x over xa times spec A. Okay. Now, so, well, a counterexample, there was part A, B, C, D, E. So counterexample, so pi 1 of, so we take A1 over, say, f p bar of t to pi 1 A1 fp bar. This map is not an isomorphism. So part D fails in characteristic P. And so here is an example. So how you can produce some covers of the affine line. The simplest example of covers is what's called Artin-Schreier cover. So this is, let's say this is K, this is K prime. And okay, so I fix some C in K prime. Consider the following cover, y equal to, so this will be over x over a affine line, over spec k prime of x. And it's explicitly, it's given by equation. So it's spec kx y, and the equation here is y to the pth power minus y is what I'm saying here, right? So sorry, yeah, it must be equal to minus c, equal to 0. Okay. So, so I consider a curve given by equation in two-dimensional plane curve given by equation y to the pth power minus y is equal to c. So then for every, this is a finite et al. Cover. Well, you just, why it's a finite et al. Cover? Because the geometric fiber, every geometric fiber consists of p points. So it's a finite morphism, and all the fibers reduced because they have the same number of points. So I claim that, so let's give a name to this. Let's call it C. And I claim that X, that these two covers are equal, isomorphic, if and only if C minus C prime is in the image of the Artin-Schreier map. So image of, no, I will write it explicitly. So a to the 5th power minus a for some a in k prime of x. So that follows from, in order to, well, in one direction it's easier. So if you have this, then just a simple change of variables shows that the two covers are isomorphic. In the other direction, it follows from Artin-Schreier lemma, which is the following assertion. If you have any field of characteristic P, then homomorphisms from Galois group of k bar over k to z mod pz is the same as the co-kernel of the Artin-Schreier map from k to k, which takes a to the 5th power minus a. So suppose you have an element of k. How you produce a homomorphism? Well, if you have an element, a in k, you find an element x in k bar such that x to the 5th power minus x is equal to a. And then you start acting by the Galois group on this x. This x, under the action of the Galois group, gets shifted by an element of z mod pz. That gives you the homomorphism. The Artin-Schreier lemma asserts that this is an isomorphism. So using this, you can even show that if this condition, if the two covers restricted to the generic point of a fine line and not are isomorphic, then this condition must hold. Okay? So for explicit example, now take C equal to Tx. And then this Tx, well, Tx is an element here, but it's not a polynomial with fp bar coefficients, and you cannot write it as a polynomial with fp bar coefficients even after adding anything of this form. Okay? Good. So now the last problem that I have 1 minute, and so so I want to use it. So there was I think the last problem, I don't remember the name. So, so construct, well, show that pi 1 et al. Of A1 over FQ bar is not abelian. Well, there are many ways of doing this. And so here is one construction which is due to Drinfeld, which is very important in representation theory. So he produced a cover of this space with the Galois group equal to SL2 of FQ. So Drinfeld's curve. So what you do, you define C as, well, spectrum of f q bar x, y. So the curve is given by equation x to the qth power times y minus x times y to the qth power equal to 1. That's the equation of the curve. So the remarkable property of this curve is that you have action of the group SL2 FQ on this curve. And the action is given by the linear transformation. So if you have a matrix A, B, C, D, then so x, y goes to A, B, C, D, x, y. Okay? So, and it's an easy computation that this equation is preserved under the action. Still, kind of. It requires a computation. I will not do it in the blackboard. And another property of this curve is that it admits a finite étale map to A1, whose Galois group is precisely this. And so this will be spec f q bar of f. And I will write down a formula for f. F is equal to x to the q squared y minus x y q squared. So the claim is that so this function is invariant under this action. Again, it's a straightforward computation, but still it's not obvious from the formulas. And moreover, if you take the quotient of C by this group, you get A1. In order to show that it's a finite étale cover, you just check that the fibers consist of the same number of points. Well, they are reduced. Sorry, you need to show that they are reduced and have the same number of points. So this number of points. So, maybe the last thing that I want to say is that why this curve is important. So you have an algebraic variety with an action of this group, and then what you can do, you can take what's called its first étale homology of C with coefficients in QA. So, and I will tell you what this is. This is just continuous homomorphisms, continuous, from pi1 étale of C to QA. So here QL is considered as a topological field. It's L-adic topology. This has also topology. So that's a general definition for any scheme. And so by factoriality, you have an action of SL to FQ here. So, what Drinif will show is that theorem is that all cuspidal representations of this finite group SL to FQ appears with multiplicity 1 in this first Littell homology of this Drinfeld curve. Well, let's say I'm interested in representations in algebraically closed field. I'm interested in complex representations. So abstractly, this field is isomorphic to the field of complex numbers. It doesn't matter which algebraically closed field of characteristic 0 I take. So what is what this word cuspidal means? Well, it means very simple. It's so this group SL2FQ has various subgroups. It has subgroup of upper triangular matrices, which is called the Borel subgroup, and it has a subgroup of well, unipotent matrices, upper triangular matrices. And that's called, well, let's call it U. And the representation is called cuspidal, irreducible representation is called cuspidal if V has no U invariant groups, vectors. So, well, if your representation, irreducible representation, is not cuspidal, so if this is not 0, then the representation is obtained, it sits inside the representation induced from the trivial representation of this unipotent subgroup by Frobenius reciprocity. So these are called principal series representations, and you have very explicit descriptions. You just take the induced representation of the trivial guy, of the trivial representation of this U, or equivalently, you can take one-dimensional representations of B, various one-dimensional representations of B coming from characters of the torus. So these representations are easy to describe, and you can compute their characters. But if you compute the number of conjugacy classes here, you see you can check that it has Q plus 4 conjugacy classes. And this construction gives you roughly half of the conjugacy class of that number. So the remaining representations are much harder to construct, and in particular compute their characters. And it's harder when 2 is replaced by larger number. And so this is one way of constructing it. For this particular group, there is a kind of other constructions, more elementary constructions. But this is the only approach that can be generalized to all Lie groups. So this was the starting point of Deligne-Lustig theory, who produced, well, generalizes the Drinfeld curve to all other reductive groups, and eventually computed all their characters of finite dimension, well, complex finite dimensional representations of FQ points of reductive groups. Okay, I'll stop here. Конечно, да. Все совершенно, да. Комплексные представления или представления в алгебраически замкнутом поле характеристики 0. Вот я знаю, что эта группа имеет Q плюс 4 класса сопряженности, я знаю, что у меня Q плюс 4 неприводимых представлений. Вот я хочу их все найти характеры, написать формулу.
Извини, я не слышал, у меня шумело. То есть ты рассматриваешь представление как конечные группы, да?
Да, да. Да, да.
Спасибо.
То есть можно строить много разных естественных конструкций многообразия, на которых действует редуктивная группа SL2. Ну, например, можно брать многообразие флагов, P1. Но, конечно, тогда что-то действует и на когомологиях, но если у вас есть связанная группа на когомологии, которая действует на многообразии, на когомологиях она будет действовать тривиально. Вот кривая c, это она таким замечательным свойством обладает. Вот там действует эта конечная группа, но это действие не продолжается до действия редуктивной группы. Ну просто вот такой формулой действует, а написать, проверить, ну давайте я... Вот я написал, какой именно формулой.
Нет, я понимаю, я имею в виду, если 2 получилось как фактор P1, почему такая штука должна действовать на таких аддитивных характерах?
Сейчас, не совсем я понимаю вопрос. Значит, вот почему SL2 действует на C или где?
Нет, SL2 действует на C, понятно.
Да.
Значит, что P1 эпиморфно отображается на SL2.
Да. Нет. P1 от A1 эпиморфно отображается на SL2. А я беру к гомологии не A1, Ага. Хорошо. Так, спасибо.